Hello everyone, this is the second episode of FlashAttention series. We already know from first episode that FlashAttention results in 2 to 4 times runtime speedup compared with standard attention algorithm. Today, we're going through FlashAttention V2, which provides another 2 times runtime speedup compared with V1. I can't wait to share with you how it's achieved. If you find this video useful, don't forget to subscribe and like. I've also opened up membership and providing free consultation for my members. Join if you're interested. Enough said, let's dive into it. I will assume my audience have already watched my FlashAttention V1 deep dive. First, let's take a look at the motivation of V2. As transformer-based LLMs need to work on longer and longer sequence, attention layer becomes the main bottleneck of scaling up. This is the main motivation for FlashAttention V1. FlashAttention V1 already shows 2 to 4 times runtime speedup compared to optimized standard attention implementations. However, this is not nearly as fast as optimized Matmul or GEM, general matrix multiplications. It only reaches 25% to 40% of the theoretical maximum flops. So this is the main motivation for FlashAttention V2. FlashAttention V2 reached another 2 times runtime speedup compared to FlashAttention V1, reaching 50 to 73% of the theoretical maximum flops. This is already pretty good considering the theoretical maximum flop is evaluated by very optimized operation including hardware optimization of matrix multiplication or GEM. So 50 to 73% is already very high. This is achieved by the followings: reduce non-matrix multiplication operations, parallelize on sequence length dimension to optimize utilization, and better execution ordering to reduce I/O, also better partitioning the work between warps to reduce I/O. I know there's a bunch of terminology that you might be unfamiliar. That's why I will spend some time to talk about GPU basics. For example, the warp might be new to some people here, and I will spend time to explain each of the items here. This is a high level of a NVIDIA GPU. There's a lot of details in this image, and I'm not gonna deep dive into it unless I have 1 or 2 hours or even more. Today, I will pick several key components and explain those, and those key components and concepts are used in FlashAttention V2. The first concept I want to go through is SMs, streaming multiprocessors, the fundamental processing units within a modern GPU. A GPU is usually composed of many SMs. Each SM is like a mini processor capable of executing many threads concurrently. This is a graph of a typical streaming multiprocessor. SMs usually contain CUDA cores or SP, stream processors. This is the fundamental execution unit for general purposes. And they usually have special units and tensor cores. These are specialized hardware for modern AI. And also there are several layers of memory, like registers, L1 cache, and shared memory, etc. The next concept I want you to know in GPU is threads. These are the smallest unit of execution. When you run a computation on a GPU, like a part of an LLM's neural network layer, usually the operation is broken down into thousands or millions of threads. And then there's the thread blocks. Threads are organized into blocks. Threads within the same block can cooperate by sharing data through a fast on-chip memory, usually it's the shared memory, and synchronizing their execution. Now let's talk about how threads interact with the memory, especially the different layers of memory. The first one is global memory, or VRAM, or HBM. It is accessible by all threads in all thread blocks and a host CPU. So it's basically accessible by almost everything on chip and on the host. While it has high bandwidth, it also has the highest latency. The global memory, HBM, has higher cost of I/O compared with SRAM. HBM is the type of technology used to implement VRAM. And this graph is showing how global memory works. This is the per device global memory, and all thread blocks can access it, and a host can access it too. The next concept is shared memory. This is a programmer-managed space that is shared by all threads within a single thread block. It provides a high-speed way for threads in the same block to communicate and share data, significantly reducing the need to access the much slower global memory. This is a single thread block, and it can access a per block shared memory. Optimizing data so we can utilize shared memory as much as possible, it is the fundamental point for FlashAttention V1. The next concept is local memory. Each thread has its own private local memory. It only exists for a lifetime of the thread, and this is generally handled automatically by the compiler, say using registers, or if the register is not enough, it will spill over on DRAM. Next, I want you to be familiar of warp and SIMD. Warp is a group of threads. Within the thread block, threads are further grouped into warps. A warp is typically a set of 32 threads in NVIDIA's chip architecture. And a very important concept closely related to warp and thread is SIMD execution. Single instruction, multiple data. This is the key characteristic of a warp, that all threads within it execute the same instruction at the same time, but on different data. This is the instruction pool. And for a single instruction within a warp, it executes the same instruction, but on different data. This means if one thread in a warp has to wait, say for I/O, often the entire warp stalls, although modern GPUs have schedulers that can switch to other ready warps. NASM's warp scheduler selects which warp gets to execute its next instruction. Now, with all those basic knowledge of GPU key components, we can take a look at how GPU optimizes GEM or matrix multiplication. NVIDIA GPUs optimize GEM through tiling, shared memory access optimization, tensor core utilization, and the use of libraries like QBLAS and CutLAS. These strategies combine to enhance data reuse, minimize memory bandwidth, and leverage the GPU's parallel processing capabilities for high-performance matrix multiplication. The first one is tiling, breaking down large matrices into smaller tiles that fit into the GPU's shared memory with better I/O. I bet this is not new to you because FlashAttention V1 is using tiling. And this graph about how NVIDIA GPUs do tiling while doing GEMs, it also looks very similar to FlashAttention V1's tiling. The next strategy is shared memory access optimization. It loads the data from global memory to shared memory with better I/O in batches and perform computations there. It probably sounds familiar too, because FlashAttention V1 is also doing similar stuff. The next is tensor core, specialized hardware with high performance matrix multiplication, especially for lower precision, FP4, FP8. So this is a very important hardware optimization for matrix multiplication. The last one is about library. NVIDIA's libraries provide optimized GEM kernels for various matrix sizes and precisions, including FP8 and FP4. So with this library, we can use Tensor Core's hardware as it full. As a result, using NVIDIA's A100 GPU as example, its maximum theoretical throughput is 312 T-flops of FP16 matrix multiplication, but only 19.5 flops of non-matrix multiplication, FP32. I pulled the data from the NVIDIA GPU specifications, and this means each non-matrix multiplication flop is around 16 more expensive than a matrix multiplication flop. So to maintain high throughput, we want to spend as much time on matrix multiplication as possible, or reduce non-matrix multiplication flops as much as possible. Now, before we move on to FlashAttention V2, let's do a quick recap on FlashAttention V1's algorithm. This is a very intuitive summary from the paper's author. For FlashAttention V1, their outer loop is on keys and their inner loop is on Q. And as we iterate through keys, the output we have is closer and closer to the actual value. And when we finish the iteration on all the keys, we should get the final accurate output for attentions. In this example, let's say the key vector has only 2 keys. So when we process key 1, we calculate S1 using Q and K1, and then we get A1 and L1 accordingly. And at last, we calculate the output with this expression. Afterward, we move on to the last key, and we do similar operations to get S, A, and L on the second position. And for O2, we have to rescale it to the correct denominator to get the accurate output scores. Now, is it possible that we're doing too many rescales since it's not matrix multiplication? Is it possible to reduce some of the operations here? The answer is yes. The first optimization in FlashAttention V2 is reduce non-Matmul flops, and one of them is to simplify the rescale. So in forward pass, we do not have to rescale both terms of the output update by diagonal matrix of L2 and save those flops. This is the O2 from FlashAttention V1. We can instead maintain an unscaled version of O2 and keep around L2 like this. And at the every end of the loop, we do scale the final O hat last by 1 over the diagonal matrix of L last to get the right output. The second way to reduce non-Matmul flops is we do not have to save both the maximum mj and the sum of exponentials lj for the backward pass. We only need to store the log sum big Lj equals to mj plus log small lj. So this is a quick comparison between FlashAttention V1 forward pass and FlashAttention V2 forward pass. And with those two very small tweaks, it reduces the non-matrix multiplication flops, and in my opinion also simplifies the algorithm. This is a summary of the forward pass algorithm for FlashAttention 2, and I have already highlighted the differences. For example, here it's when we scale output at the end of the loop, so we have the accurate output. And here is we write big Li to HBM directly instead of storing M and small l. For backward pass, it's not that different compared with FlashAttention V1. I've also highlighted the differences here. The first one, it's not exactly reducing non-Matmul, but by pulling the computation for D ahead as a whole big chunk, it is indeed more efficient than FlashAttention V1. And this is where we tweak the algorithm a bit to use big Lj instead of mj and small lj, corresponding to the forward pass. Now let's move on to the second strategy FlashAttention V2 use. It's better parallelization among thread blocks. FlashAttention V1 parallelize over batch size and number of heads. So there are overall batch size multiplied by number of heads thread blocks. Each thread block is scheduled to run on a streaming multiprocessor. Using NVIDIA's A100 GPU, for example, there are 108 SMs, so computations scheduled on different SMs are executed parallelly and require no synchronization between them. Scheduling is usually considered efficient when this number is, say, larger than 80, since the total number is around 108, to effectively use almost all the compute resources on the GPU. However, in the case of long sequences, which is very common in today's advanced LLM, this usually means small batch size or small number of heads due to GPU memory limits. So this number is going to be small and GPU is not utilized efficiently. To have better GPU parallelism, especially on long sequences, FlashAttention V2 additionally parallelize over the sequence length dimension. This means there will be batch size multiplied by number of heads multiplied by sequence length thread blocks needed, and it will definitely be sufficiently large even when batch size is small for long sequences. Now, other than additionally parallelize over the sequence length dimension, FlashAttention V2 also changes the order of execution for forward pass. During forward pass, FlashAttention V2 parallelize by assigning each worker a block of rows from the query matrix, and each worker then computes the attention output for its assigned queries independently. And if you remember, each row represents a single query. And in FlashAttention V1, we were iterating on keys on the outer loop. However, on FlashAttention V2, the outer loop will be iterating on the query dimension. Worker 1 takes the first block of queries and compute their attention output by attending to all the key value pairs. And worker 2 simultaneously takes the second block of queries and does the same. And this continues for all workers. The row represents the queries and the column represents the keys and values. Each colored block shows a worker processing its set of queries against a corresponding block of keys. And the white means causal mask. If you're not familiar with the causal mask in Transformer, take a look at my Transformer deep dive. Since the attention output for each query is independent of the others, there is no need for communication between workers in the forward pass, making this highly efficient. Again, I highlighted the difference on the reversal of ordering. In the outer loop, we are now iterating on queries, and in the inner loop, we are iterating on keys and values. This is the opposite of FlashAttention V1. And this GIF did a great job on demonstrating how FlashAttention V2 works. I pulled it from max.com. Hope it helps you to understand intuitively. We are iterating on the outer loop on queries, and within each query, we iterate through all the keys. Now the backward pass involves calculating the gradients of the query key and value matrices, which is key for training the model. Here the parallelization strategy shifts. Instead of splitting the queries, FlashAttention V2 parallelize over the key and value pairs. This is the same as V1. Each worker is now responsible for a block of columns of the attention score matrix. This means each worker calculates the gradient contribution from a subset of the key value pairs to all the queries. Worker 1 processes the first block of key value pairs and their influence on the gradients of all queries, and worker 2 handles the second block, and so on. So we already know for forward pass, swapping the order is actually great for parallelization because for each query, there's no communication within each other. So for a single worker to process row simultaneously is a great plus. Why can't backward pass do the same? This is because, unlike the forward pass, the backward pass requires some communication, and we use atomic operations for those communication between workers to correctly aggregate the gradients for the query matrix. However, this column-wise parallelization is more efficient for the backward pass as it reduces the amount of data that needs to be communicated. The only shared computation between different column blocks is in updates DQ, where we need to load DQI from HBM to SRAM, then on-chip update DQI and write back to HBM. This is the part I've already highlighted it. So we achieve this by scheduling one thread block for each column block of the backward pass and use atomic as to communicate between different thread blocks to update DQ. Now we have gone through the optimization between different thread blocks. The last optimization I want to go through is how FlashAttention V2 partition a work within a single thread block. Note that the paper's author is using 4 warps per thread block, thus the graph here, pulling from the original paper, is also using 4 warps per thread block. FlashAttention V1, which is the graph on the left, splits K and V across 4 warps. This is within a single thread block, while keeping Q accessible by all warps. Each warp multiplies to get a slice of QKT, then multiply with a slice of V, and communicate to add up the result. This is inefficient since all warps need to write their intermediate results out to the shared memory, synchronize and add up the intermediate results. These shared memory writes slow down the forward pass. FlashAttention V2 instead splits queries across 4 warps and keep key and values accessible by all warps. After each warp perform matrix multiplication to get a slice of QKT, they just need to multiply with their shared slice of V to get their corresponding slice of the output. There's no need for communication between warps. The reduction in shared memory reads-writes contributes to runtime speedup. FlashAttention V2's backward pass has similar partition, but it still requires some synchronization between warps. The synchronization we already have gone through in previous slides. Alright, this is the last optimization strategy for FlashAttention V2. I hope this video is helpful to you. If you find it useful, please don't forget to subscribe and like. Alright, see you next time. Bye.